Hello and welcome to Project Liberty Light, the Living Flag Project, Part 3, Power, Control, and Management. Up until now, we've focused on getting the LEDs working and adding control, but now it's time to power the system the right way. It's time to take the next big step. In this part, we're going to add a rocker switch to safely control the system and improve power distribution and stability. For this build, we're using a 5-volt, 5-amp DC power adapter and a 2-terminal on-off rocker switch that should be rated for at least 6 amps. The switch that I'm using is rated at 10 amps at 125 volts AC and at 10 amps at 250 volts AC. Even though the switch is rated for AC, it works perfectly for our low voltage DC application and gives me a rugged, reliable way to control power. Up until now, you've likely been powering the system by plugging and unplugging it. That works fine, but it's not ideal. A proper power control system gives you a safe startup and shutdown, better control during testing, a more professional build, and protection for your components. In real electronics projects, power control isn't optional, it's essential. The first thing that we're going to do to update our circuit is to add another capacitor. In the previous parts of this build series, we had connected a 1000 microfarad electrolytic capacitor across the positive and negative power rails of the breadboard. That capacitor is meant to be near the LEDs, but for the time being was placed as it was on the breadboard in part 1. Do not remove this capacitor, we're going to still use it. We also need to add a 0.1 microfarad capacitor to our system for noise filtering. These capacitors will help prevent flickering LEDs, random resets, and voltage spikes. I want to place this new capacitor near the 1000 microfarad capacitor I added to the breadboard in the previous part of this build series for the LEDs. I placed the leads or legs of the 0.1 microfarad capacitor straddled across the center groove of the breadboard. One leg of the capacitor is at point 2E, the other leg of the capacitor is at point 2F on the breadboard. I connected the capacitor's legs to adjacent points on the positive and negative power rails using jumper wires. Earlier in this project series, I had connected the 5-volt pin and a ground pin from the Arduino Uno to points on the positive and negative power rails of the breadboard. I had placed the yellow jumper wire from the 5-volt pin of Arduino to a point on the positive power rail of the breadboard, and a white jumper wire from the ground pin of the Arduino to a point on the negative power rail of the breadboard. Each of these jumper wires were placed near a 1000 microfarad electrolytic capacitor I established across the power rails. The capacitor was for the benefit of the LEDs to prevent flickering when power was added to them. I now want to relocate those 2 jumper wires somewhere further down the power rails. It doesn't matter where. I'm just doing this because I intend to place the new power supply being added here at those points near the capacitors where the Arduino's jumper wires were. As for adding the rocker switch to the circuit, the goal here is simple. We want to interrupt the positive line so we can turn the entire system on and off. The basic concept is the power supply positive goes through the switch and the power supply ground goes directly to the system. An important thing to note here is to always switch the positive line, not the ground. We also want to add a mandatory fuse for protection. Since we're adding a proper power switch and using a 5-volt, 5-amp power adapter, there's one more critical piece to include, and that is a fuse. A fuse protects the system from short circuits, wiring mistakes, component failure, and excessive current draw. Without a fuse, a fault in the circuit could damage your LEDs, it could damage your Arduino, overheat wires, and potentially create a fire hazard. A fuse is a sacrificial safety device. It fails before your system does. This is exactly what we want. As for choosing the right fuse for this project, the things that we know is that the power supply that we're using is rated at 5 volts, 5 amps, and the LED system, it's theoretically maxed at approximately 7.6 amps. So the recommended fuse size for this particular project is to use either a 5 amp fuse or even a 7.5 amp fuse, but I would recommend using the 5 amp fuse, and for this build a 5 amp inline fuse is going to be ideal. The fuse must be placed in series with the positive line before the switch. The power path should go from the power adapter to the fuse to the rocker switch and then finally to the system's 5-volt supply. In this case, the positive power rail of the breadboard. The ground still goes directly to the system, and in this case, the negative power rail of the breadboard. Most 5-volt DC adapters, such as our 5-volt DC adapter that we're using for this project, follows the standard of the red wire and center pin going to the plus 5-volt supply or positive supply, and the black wire and outer sleeve of the adapter goes to ground. If using a barrel connector, the inner pin is the plus 5 volts and the outer sleeve is the ground. It's preferable that we don't have to modify the power adapter cord in any way to add a switch in between it and the system. What I chose to use was a center positive female DC power jack socket to allow me to plug the power adapter into the system with ease, then place the fuse and switch between the socket and the system. The power adapter's barrel connector will plug into the female DC power jack socket. The red wire of the female DC power jack socket will then be connected to the inline fuse before the rocker switch, and then the black wire of the female DC power jack socket will connect to the system's ground. And in this case, I'll just wire that black wire to one of the points on the negative power rail of the breadboard. The 2-terminal rocker switch is simple. One terminal goes to the inline fuse, and then the other terminal will get connected to a jumper wire that will be added to a point on the positive power rail of the breadboard to feed in the plus 5 volts from the power adapter. That's it, no polarity concerns on the switch itself. Another thing to note is that we do not run ground through the switch. Instead, we're going to run the ground of the power supply to the common ground of the system. The black wire from the female DC power jack socket to a point on the negative power rail of the breadboard near the 0.1 microfarad capacitor. The connection made by, in my case, a black test hook jumper wire. The ground is distributed to both sides, both negative power rails of the breadboard through a blue jumper wire, creating the common ground of the system on the breadboard. All grounds must meet or connect to each other as one, a common ground made on the negative rails of the breadboard. The power supply ground goes to the negative rails of the breadboard, the Arduino ground goes to the negative rails of the breadboard, and the LED matrix ground goes to the negative rails of the breadboard. The rocker switch output, the plus 5 volts, gets connected to a point on the positive power rail of the breadboard near the 0.1 microfarad capacitor. This power supply gets distributed to both sides, both positive rails of the breadboard, through an orange jumper wire. From there, power is distributed to the Arduino 5-volt pin and to the LED matrix plus 5 volts. So just as an overview of what we're looking at here, we have the DC, or the female DC adapter. We have the negative coming from the outside of this adapter here. The black wire is attached to that outer casing. And then I have this green jumper wire going around to this blue jumper wire going to a point on the negative power rail of the breadboard, where that negative power rail is distributed to both sides of the breadboard via this other blue jumper wire and distributed up this side. The center positive pin of this female DC power adapter is connected to this red wire, and the red wire is connected by a jumper wire, and that jumper wire loops around here and is connected to this end of this inline fuse. and the inline fuse continues over to this red jumper wire, loops around here, and goes to this side of this rocker switch. And on the other pin of the rocker switch, there's this red jumper wire that loops around over to this orange jumper wire to a point on the positive power rail of the breadboard, and that positive power rail is distributed to both sides of the breadboard via this orange jumper wire, which continues up this side of the breadboard. And remember, although it's hard to see, we put this new 0.1 microfarad capacitor within the circuit on the breadboard, and I have one leg connected to a point on the positive power rail, and the other leg or lead of that capacitor tied to a point on the negative power rail. And all the other wiring, it looks like a mess, but all the other wiring is exactly the same as we've done in the previous videos or previous parts of this build series, so nothing else has changed. Just to note a few important safety notes here. As for the switch rating, the rocker switch that I'm using states that it's rated for 10 amps at 125 volts AC and 10 amps at 250 volts AC. In a 5 volt DC system drawing approximately 5 amps max, this switch is more than sufficient. As for current considerations, the LEDs of the matrices I'm using for this project can draw significant current. For the WS2812B matrices that I'm using for this project, they are at about 60 milliamps per LED. That's for full white color LED. And there's 128 LEDs, so the theoretical max or maximum of amperage draw, it would be around approximately 7.6 amps. But I'm running reduced brightness in the code, so the real usage is going to be much lower. With the 5 volt, 5 amp adapter I'm using, plus the brightness limit I've set in code, this should provide a safe operating range. And we're not going to be updating the code at all in this part of the series. The code is as it was or where we left off in part 2. And if you go back and look at that code that was provided there, we did go over about the brightness limit that we set in code, and nothing has changed from there. I also want to note that the fuse must be on the positive line. Never place the fuse on ground. The fuse should be close to the power source. This protects the entire wire run, not just the load. And we never want to bypass the fuse. If it blows, fix the problem, don't skip it. By adding a fuse and switch, this project now includes controlled power through the switch, protected power through the fuse, and stable power through the capacitors and grounding. Adding a fuse might seem like a small step, but it's one of the most important upgrades you can make. It protects your build, your components, and your workspace, turning your project into something that's not just functional, but responsibly engineered. So as I mentioned, there are no code updates. The power switch operates independently of the microcontroller, meaning no code changes are required. This is just a hardware level control, just like in real embedded systems. At this point in the build, we've made one of the most important upgrades to our Project Liberty Light system. We're no longer just powering our circuit, we're controlling and protecting it. So far, Project Liberty Light has been all about visual impact, but in the next part, we're going to take things a step further. We're adding audio. In part 4, we'll explore how to integrate a speaker module into the system, play simple tones or preloaded audio, begin syncing sound with light behavior, and lay the groundwork for more immersive effects. Imagine your LED display not just showing a flag, but coming to life with sound alongside it. This upgrade may not change what your LEDs display, but it completely changes how your system behaves. You've taken a big step from a working prototype toward a dependable, real-world build, and that's what engineering is all about. I want to thank you for joining me for this part of this build series, the Project Liberty Light build series. I hope you've been enjoying it so far. Can't wait to see you in the next one, and remember to keep at it and stay motivated.